Okay, so on 68, we want to reduce this and list the excluded values. Okay, so 1, I'm going to call this b of x because I don't want to keep writing it down. Okay. This actually does get used for something. The reason I asked this question is this thing's called a Blaschke product, which gets used for math.
But for what? Isn't it just x over x minus 10?
When you want to punch a bunch of holes in something, this is how you do it. So it is, all right, let's see. So if we just start crossing stuff out, right? Let's see. I'd cancel this and this, right? And this and this.
And 3 and 3
And that and the 3, and then there's a bunch of these, right? Is the x minus 8 going to get canceled?
Yes.
Yeah, by the bottom of the previous one, right? And then the x minus 9s will get canceled. And so I'll get, right, that b of x is x over x minus 10, right? Except
when x equals 2, 3, 4, 5, 6, 7, 8, 9.
that's what I want to hear.
Gotcha.
So when I think about the domain of this thing, right? I kind of think here, this thing has a domain,
So everything in between the numbers, but not the numbers themselves.
right? And the domain of this guy is numbers except the ones that make me divide by 0, right? And the ones that made me divide this formula by 0 are 1, 2, 3, 4, up to 10, right?
Because 0 times all of those is still 0.
Including 10 or?
Yeah, including 10. But the domain of this guy, right?
Is just everything except for 10.
Exactly. So the domain on this guy is R except 10, right?
Okay, that's not hard.
So b of x is equal to this thing except at, so where isn't that thing this thing?
1,
1, 2, 3, 4, 5,
Yeah,
6, 7,
all the
8,
other
9.
all the holes I plugged, right? Except that x is 1, 2, up to
9.
9. You get to see that? So when the book asked for the excluded values,
Well, except in the book it's also 10.
yeah, so they're asking really for what's the domain of the function. These are the holes I plugged, right? Oops, plug. Right, the holes plugged by reducing, and this.
So if you have a machine firing bullets every point, then this would be to figure out which points the bullets don't hit.
So this is like, I want to go through and systematically remove a bunch of points from the domain, right? So this is a way to take, okay, this is a function I know about, right? It's got a hole, or it's got an asymptote at 10, but I want to go through and punch holes in the integers between 1 and 10.
It's like adding posts to like a fence or something, adding a middle post
Mhm.
between.
So if you
Yeah, so here we're going through and we're going, all right, we'll take those values out, right? If I hadn't put the stopping dots on this, right? Like if we hadn't stopped here.
then it would be everything except for like all real numbers.
So-
except for all real numbers.
Let me kind of modify, right? So if I modified my b of x and I said, all right, this is x times x minus 1 over x minus 1 times x minus 2 over x minus 2 times x minus 3 over x minus 3. You guys see what I'm doing? So each of these multiplications is 1 everywhere except at that point. Right? So this is 1 except at 1. So this guy here is a hole at 1.
Okay.
right? I'm punching a hole at 1 by multiplying by that. I'm punching a hole at 2
So
by
that's
multiplying by this
0,
one.
1, 2, 3, 4, 5, 6, 7.
So if I just dot, dot, dot this process without letting it end, right, the book stopped. But if I just dot, dot, dot it, then what have I got?
Nothing.
Well, I've punched a hole at every natural number, right?
So all
But
real
there are
numbers
a-
except for natural numbers.
Uh-huh. So this guy has domain, right? B hat has domain R except the naturals. You see that? And I can actually even graph this function. What was the function I started with before I started punching holes in it?
X.
You guys all see that? It started with b of x is x, and then I punched a hole at 1, 2, 3.
Well, technically, doesn't that punch a hole at 0 as well?
No, because I didn't ever divide by x, right?
Okay.
So I started out with the line, right? This was y equals x, really. So this is 0, 0. Here's 1, 1. This is what I started with. But then I said, okay, well, we'll punch a hole there. So there's a hole. Then I said, okay, we'll punch a hole at 2 as well. So there's a hole. You guys see this kind of weirdness? This is what a Blaschke product does.
It's definitely just-
It's super bizarre that you can kind of go through and do this, but this is a way to do it. It's just to keep multiplying by these ones, they just punch holes. You see that?
So if you were like, no, no. Like what would this graph, like a whole bunch of magnetic fields holding together, just the magnets aren't actually touching because of the way that they're held together, or?
So let's see, what would I use something like this for? So the traditional use of these is, well, at least my thought on the traditional use is that you use them proving things. They're just a good way to go through and systematically punch a bunch of holes. But I'm not sure what the applied guys use them for. I know they get used for something.
Or like bugs, if a bug
I've
keeps-
I've seen the idea of a Blaschke product in an applied math book, so they use them for something that's not here. I don't know what that was. I don't recall. But the use that I've seen of them most often is you want to go through and remove a bunch of stuff from consideration. So you just multiply by one of these Blaschke products that just zips it all out of the
or if you
domain.
have like a tire that has